Hi everyone, my name is Clarissa Lopez, and for our senior project, we worked on the smart grid model with Dr. Monemi as our advisor. And there are 6 of us in total who worked on this project, which would be myself, Katrina Robles, Brooke, Nguyen, Tristan, Vacheron, Balsam, Boudiab, and Ulysses, Perez-Ramirez. So before I begin, I just want to go over a quick overview of what we will be discussing in this presentation. So first I will talk about what is a smart grid and then its brief history. Then the other students who worked on this project with me will then talk about the issues we came across while doing this project, the solution we came up with, and finally the future plans for the smart grid. So first and foremost, what is a smart grid? Before we can answer this question, it is important to understand what an electric grid is. An electric grid is a network of transmission lines, substations, transformers, and other components that contribute in safely delivering electricity from a main power source, such as a power plant, to customers. So in this case, a smart grid is an electrical grid that uses information and communication technology to gather and act on information. Power companies use smart grids in their design for power grids in cities in order to examine the amount of power that may be used in a day. So now we go through what students have done on the smart grid model for the past few years. So the smart grid model was first developed in 2016, and this original model contained industrial, commercial, and residential loads. But in 2018, the students replaced one of the industrial loads with a substation system. And finally, in 2019, the students implemented a hospital. In order to do so, they had to completely remove the industrial loads as well as some of the commercial loads. And here's a picture of what the smart grid model looks like currently.
Upon initial inspection of the smart grid, we found 3 issues. The issues were that the system did not turn on, there was a lack of proper documentation, and there were a lot of loose and disconnected wires throughout the grid. In the beginning of the year, we tried to turn on the smart grid according to the instructions created in a previous year. However, the terminal, which is the display screen, would not turn on. We also noticed some other individual components not turning on, such as LEDs. This led us to opening the lid of the smart grid, and upon a closer inspection, we found a lot of loose and disconnected wires, messy wiring, and a few burnt out components. The picture on the slide is an example of the initial condition of the smart grid. We thought that we could use previous schematics and wiring diagrams to help us fix the wiring. However, there was very few documents available to us. So how did we solve these issues? We created a plan of action for our project, which included creating a master wiring diagram and upgrading the wiring. We felt that a master wiring diagram and upgrading the wiring were essential and necessary for the safety of the smart grid and its users. In the following slides, we will be discussing how we created the mastering wiring diagram as well as how we upgraded the wiring.
So now I will be talking about how we went through the process of creating the wiring diagrams. In order to do this correctly, we had to do reverse engineering to determine what the functions are for the sections of the smart grid and its components in relation to the whole smart grid model. Reverse engineering is the process of dissecting a product to learn how it works. In this case, we did reverse engineering by looking into each part, reading its pinouts and manuals. This was also very important when drawing out the parts on the diagram. So as you can see here, this is a pinout we found for the Arduino Nano. We use this as a reference to figure out what each port is, and we also use this as a reference to draw out this part, which is on Arduino Nano, on the diagram. This then leads me to my next point. Which software do we use to draw? Our initial idea was to use AutoCAD primarily because of its versatility. However, we ultimately chose to use PSpice because a version of the program can be installed for free, which makes it more convenient for sharing and passing down the drawings to the next group of students who will be working on the smart grid as their senior project. I was actually the one in charge of drawing everything on PSpice, and here are some of my drawings. We tried to make everything as uniform as possible. I'm talking about how we label different parts or even the file names. So for example, in this drawing, you can see T1A. The first letter is T, which means that this is a transformer. The next character is number 1, which means that this is in section 1. The last character is letter A, which means that this is the first transformer. Generally, this is the kind of standard that we use all throughout our drawings. For example, we use T for transformer, R for relay, P for PCB, and for microcontroller, C for connector, and G for ground bus. In this drawing, you can see R3A, which means that this is the first relay in section 3. We also use a format in naming the drawing, so as you can see in the bottom right, this drawing is named 307. The first number indicates which section it belongs to, so that is in section 3. The last 2 digits refer to the number of page in that section, so basically 307 means that this is the 7th drawing in section 3.
Now we will be discussing how we fix the wiring.
So when we first started dealing with the smart grid and opening it up and seeing what it looked like under the lid, we noticed that the first thing we noticed was the wires were just all over the place in a state of general disorganization. And it seemed like the previous generations that had been working again and again on the smart grid hadn't put a whole lot of thought into how it should be organized. And probably as a result of that continued disorganization, a lot of the wires had become tangled and several had become loose just over time. And we noticed that some parts and circuit elements were non-functional. There was one particularly bad example in section 5 where a circuit element on a PCB board had burned out completely and needed replacing. And we came to the conclusion a lot of this was due to kind of the way things were organized. Like in this picture, you can see here is one of the sections where we thought that the space being used was not efficient enough, and we wanted to make it more centralized. And as you can see from here, from a bird's eye view, it's a lot easier to see what's going on here. And so that's how we kind of based the redesign for each section, was so that everything was more efficient. The wires are a lot shorter, so there's no chance of it getting tangled or any kind of confusion. And that's the kind of goal we had when reorganizing the wires.
To continue on with section 2, you can see just how unorganized the wiring and the placement of the relays were. To fix this, we reorganized the placement of the boards, including the relays and the microcontrollers, and reorganized the wiring. In section 3, the residential section, you could see on the left-hand picture, the before picture, that it was extremely unorganized. And to correct this, we reorganized the placement of the relays and the PCB boards, including the transformers, and placed the wiring in plastic conduits to organize the system. In section 4, you can see the circuits and how they're all jumbled together. And to fix this, we separated the PCB boards and organized the wiring and separated some of the circuits to be in this section and in the other section.
By bringing in PCBs closer together and shortening wires, we were able to generate space in section 4 to implement a new idea. We could implement protective relays. Protective relays are a device that are designed to trigger a circuit breaker when a fault is detected. This brings the benefit of protecting equipment against faults, such as short circuits, and it could also isolate faulty equipment. The protective relays are going to be placed inside the distribution substation. As you can see in here, we have circuit breakers, and every circuit breaker along the high side and low side, as well as the distribution lines going to our loads, are going to have the protective relay. So this is a block diagram of one of the, as an example, for one of the lines that come out the distribution substation and go into the load. So the predictive relay works like this. It consists of a current sensor and a relay, which is normally closed, as well as a microcontroller. So as power flows from the distribution to the load, the current sensor will be sending the readings to a microcontroller. The microcontroller would have a threshold value where it would open the relay when the current sensor measures a value that hits that threshold. Once the threshold is met, the relay will open and no more current will be flowing through, thus allowing the, the protection for a distribution substation.
So, in conclusion, in this presentation, we went over what an electrical grid was, a brief history of the smart grid model, the issues we encountered, the solutions we came up with, and our future plans for this project. We hope you enjoyed learning about our project and electrical grids. Thank you.